Hello Internet, Jordan here. A prime number is a number where the only way to make it by multiplying numbers together is to use the actual number. So for example, 10 is not prime because 10 is 2 times 5. And neither 2 nor 5 is 10, obviously. But 11 is prime because the only way to make 11 is 1 times 11. You have to have the 11 in there. There's no way to break it down into factors. So that makes 11 a prime number. Now, the bigger the numbers are that you're looking at, the less there is a chance that they're going to be prime. Primes become more rare as you go through the number line, you look at bigger and bigger numbers. And that's simply because as you look at bigger numbers, there are more numbers less than them, so there are more numbers that they could potentially be divisible by. That doesn't necessarily mean they'll actually be divisible by them. The prime numbers never end, but it does mean that the primes become more rare. So the probability that a number, if you just pick a number at random, is going to be prime depends on how big the number is. So is there a way to figure out what the probability is that any given number is prime based on how big it is? Well, it turns out that yes, there is actually a way. It's called the Prime Number Theorem, and it's very important in mathematics. The Prime Number Theorem. Here's how it goes. If I have some number, we'll call it n, the probability that n is a prime number is 1 over the natural log of n. Now, don't worry if you don't know what natural log means. There's probably a button for it on your calculator anyway. We'll get to that here shortly. But that's it. That's the rule. This is the probability that any given number is prime. It really is just that simple. Okay, so now that we know that the probability of a number around n being prime is 1 over log n. By the way, when I say log, whenever I say log, I mean the natural log in this video. Just wanted to clarify that. So if the probability of n, or a number around n being prime, is 1 over the natural log of n, there are a few other things we can say just based on this. So first of all, the number of primes less than n is probably going to be about n over log n. So if chance of a number around n being prime is 1 over log n, the number of primes less than n is probably about n over log n. And what this means as well is that the average gap between primes less than n is about, that's not what I meant to write, I just combined the 2 letters into 1 there. There we go. The average gap between primes less than n is about the natural log of n. So that's just a natural side effect of this rule. And there's one more thing we can say as well. We can kind of use this rule in reverse. The nth prime number is about n times the natural log of n. It's about n log n. So once you know this, the chance that a number is prime, you can then make all of these related statements just by following the rule and seeing what happens. So let's now see an example of this rule in action, because I haven't yet shown you how accurate this is. So let's get rid of this, and we'll see an example of this rule in action. So let's say that n is 1,000. Let's take n equal to 1,000. 1,000's a nice big number. It's good for this sort of thing. Actually, the bigger the numbers are, the more accurate this becomes. So that's an important point right there. So if we take n equal to 1,000, 1 over log 1,000 is around about 0.145. So what this means is that about 14.5% of numbers around 1,000 are prime. So some numbers around 1,000, let's say from 900 to 1,100. There we go. That gives us 100 numbers on either side. That'll give us a nice sample size. So we have 200 numbers here that are all in the vicinity of 1,000. So let's apply the rule. So we know that about 14.5% of numbers from here to here should be prime. So if we multiply the 200 numbers in this range by 14.5%, the answer we get is that there should be about 29 prime numbers from 900 to 1100. So, how many are there, actually? How many prime numbers are there from 900 to 1100? The answer is 30. We're very close. We're very close with this estimate. The prime number theorem is almost startlingly accurate sometimes. All right, now that we've seen the prime number theorem, I think I should probably talk about what natural log means, because I kind of just glossed over that before. So the idea behind natural log is it's actually quite simple. It's not that hard. You just need to know about this number. And so I'm going to tell you about this number called Euler's number. We often write it with the lowercase letter e. So it's named after this mathematician named Euler, very famous, very influential mathematician. He came up with the idea, well, he didn't come up with the idea, but he was the first one to actually calculate it, this number that we now call e. And the idea behind e is that you figure it out, or you get an approximation of it, by taking 1 plus 1 over something, let's call it x, to the power of that something. So let's use 5 as an example. If I take 1 plus 1 over 5, that's going to be 1.2, right? 1 1/5. If we then raise that to the power 5, that gives us an approximation of Euler's number. But it's not a great approximation because 5 is a small number. So this comes out to be 2.48832. Whereas the actual value for E is 2.71828, and so on. It's irrational, it never ends. But the bigger the number you use, the bigger your value of x here, the closer you get to this actual number that we call e. So that's what Euler's number is, and it's super important in math, shows up all over the place. What the natural log does is it asks, what number can I raise e to the power of to get whatever number I'm looking for? So earlier we used the natural log of 1,000. So if I take the natural log of 1,000, what that means is what number can I raise e to the power of and get 1,000? So e to the power of what number is 1,000, and that's about 6.9. So it's usually not a whole number. If you put a whole number in and you take the natural log of the whole number, it's definitely not going to be a whole number. And that's just because e is irrational. But that's the idea behind the natural log. Any number is e to the power of something, and so the natural log just tells you that something. Again, not too complicated as functions and mathematics go, but it says some really interesting things about the prime numbers. And there you have it. That's the prime number theorem. The prime numbers, they seem random at times, they seem like they don't follow any patterns, but they do follow patterns. They actually follow a lot of patterns, and the prime number theorem is one of the nicest prime number patterns there is. Hope you enjoyed learning a bit about it, and thanks for watching.